Well, good morning, everybody. We seem to be a few short this morning, so maybe they'll come in later. I don't know. If you remember, we were talking about cathodic protection. Basically, our pipelines, whether they're offshore or onshore, are exposed to an environment, and that environment is either offshore seawater or the seabed moisture, or onshore the groundwaters in the soil, or the environment, the atmosphere and sunlight and so on if they're above ground. So they're all exposed to some sort of environment, and the way we look after them is to coat them and also use cathodic protection systems. And we started looking at the sacrificial anode systems, the galvanic corrosion effect essentially, and we went through their advantages and disadvantages. And one of the main problems with the sacrificial anode system is that the applied voltage is never very high, and so the resistance effects in the system become significant because all these systems obey Ohm's law. So we've got I equals V over R, and if V isn't very big and R is big, then you can't get much current. So it's a problem for those systems, and they're actually better applied in the offshore situation or in highly conductive soils. So we talked about sacrificial anodes. I think we also talked about the general factors. Is this a slide you recognise? No? Okay, right. So this is just a note about the overall electrical resistance and making sure that R is low so that we don't get too much potential drop across the system. And we used a combined CP coating situation to slow the rate of loss of sacrificial anode, or to save on power consumption in the case of the impressed current systems. So as well as using insulating protective coatings to try and isolate the pipe from the environment, we also use insulating joints to try and compartmentalize, if you like, try and break up the pipe section so that we can cathodically control it. So for example, quite a lot of the pipe is buried underground, and then it will come to the surface where you've got a pumping station. Above ground you don't need the CP. You've also got the compressor and various other bits of electrical kit in the pumping station. You don't really want the system, the cathodic protection system, to be linked through the compressor area. So you put insulating joints in so that the above ground facilities are not linked to the CP system. And that allows you to get better control of the buried component. And we'll come back to insulating joints briefly later on. Okay. This slide I think you've had. Yeah. So this was just to start the impressed current side of things. So we need a DC power supply. Sometimes the power supply is quite sophisticated. It has potential measurement feedback on it. Sometimes it's got a data logger on it, which will record the potential of time. We don't want to lose current from anywhere if we can help it, so we will need to insulate the supply leads to the pipe. We need to make sure those connections are good, and they're usually thermit welded to the structure so that there is no weld defects, significant weld defects, or complex microstructure in the electrical connection. The DC power supply is usually rectified mains, but that rather depends where you are. If you're out in the middle of nowhere, you might use solar power or even wind power and a battery pack. And one of the problems with renewable energy, of course, is it's only available at certain times, in the daytime for solar power, when the wind's blowing for turbines and so on. So you need a reasonably sophisticated storage system with these batteries to ensure that you've got continuity of power during the night or when the wind's not blowing. but they are now quite feasible. This is just a electricity main supply box with rectifier, a steel lockable cabinet above the pipeline for supplying power to the anodes, and as well as the anodes and the connections to the pipe to the power supply, you also put in additional test points to monitor the potential along the pipe. If you're in the middle of nowhere, you don't need those very frequently. Every 3 kilometres or so, it's fine. If you're in a built-up area, then you need them a bit more regularly positioned, because there are other pipes in the area, there are other things happening in the area, and even if the area appears reasonably quiet at installation, things change all the time. Somebody goes and builds a new pipeline and going across yours, or they do some earthworks and change the water table level so that the resistivity of the soil changes, or whatever. So you need to know what's going on in your built-up areas, so you put the test points a bit close together, and then you put them in all these other positions as well. So anywhere where there's likely to be stray currents from other CP systems, from electric trains, from where there is changes in water table level, etc., etc. So test points are useful things in the design to check the potential on the pipe. This is just a little collection of photos of test points. So all we're doing is measuring the voltage between the reference electrode and the pipe, and there are that's a hatch with a lead coming off the pipe. This is another version of test point. So it's important to monitor the potential over time, and there are various recommendations as to the frequency of that. We'll come back to it. Okay. This is the anode installation side of things. Basically, you've got two options. You can either lay the anodes out horizontally, sort of parallel to your pipe structure. Often the pipe will be tens of meters away from the anodes, and we'll discuss that a little bit more later. Alternatively, you can drop the anodes in vertically, and that works pretty well. The field distribution, the potential gradient that you get from the anode to the pipe works pretty well in both orientations. These ones here, they can't particularly tell from the wrap, are silicon ion anodes, and once you put them in the trench, I don't know whether you can see here, but it's quite dark in the bottom of the trench, and that's because they've already put some coke in as backfill, so they increase the conductivity of the trench by adding carbon, effectively, and coke is cheaper than a lot of other things, so you just backfill the whole thing with a cheap supply of enhanced conductivity material, and that allows you to get a better potential distribution and current flow. Okay. Give you that next. As you might imagine, in terms of labour, it's a little bit easier to bore a vertical hole than to dig a long trench. And of course, if you're in an urban environment, the chances of being allowed to dig a long trench are slim, so it's advantageous to dig selective holes with a borer. So there are various reasons why you might choose one or the other option. And again, you can backfill part of this borehole with conductive medium. What's come round on the handout is this basic CP system. So we've got our DC power supply, we've got direction of electron flow, and don't forget that's the reverse of the current flow. The current flow is going anti-clockwise around the system, the electron flow is going clockwise around the system. And this always causes great confusion. Some years ago I had a Royal Naval engineer sent back to university to sit in on these lectures because he had incorrectly wired the CP system on his boat and dissolved a hole in it. And he was not popular, as you might imagine, with the commander, and was sent back to get a good lecture about electron flow and current flow. And it is a bit tricky to think about the wiring on these things. Typically, the distance between the anode and pipe is in the order of 100 meters or so. Okay, we're not putting the anode and cathode close together because we want a throw of current, a more even distribution of current across the length of the pipe. Okay, so the distance between anode and cathode, 100 meters or so, and then the distance between the power supply units can be 10 kilometers or so. So there's quite a big gap between supplies connected to the pipe, and in between those are the test points. So we've got 10 or so test points between each power supply location. So really the anode pipe distance, instinctively you'd say, oh well, to keep the resistance down, we'll put the anode and cathode close together. But in fact, in order to get a more even current distribution, you have to move the anode and cathode apart a bit. Yes, sir.
Bigger the pipe diameter, bigger will be the installation.
Yes, that's well. We're going to do later on. We're going to look at the current calculations. But you're right. The current that you require relates to the surface area, and that relates back through to your number of anodes and power supplies. So you can scale it up.
A question about this. So if you're talking about, you're saying like the cathode and anode is about 100 meters apart.
Yeah.
So as long as the protected structure, like the pipeline, is within the 100 meters, the entire pipeline is protected, or must the entire pipeline be?
So every 10 kilometers or so along the pipe, you've got a connection and another power supply. Okay. So this is about 10 kilometers. Okay. And one of the reasons why you don't need them closer together than that is because this is a coated pipe. And so really all you're doing is the current flow isn't large unless you start getting defects in the pipe coating, and then it gets more exciting.
So in your example, you just need one anode.
This is, because it's a cross section and the pipe's going this way, you can't see the next anode.
Yeah.
Yeah. You very rarely have a system with just one anode in it. You get multiple anodes along the length.
So in this example, for every 10 kilometers, how many anodes do we expect? Or do you have the calculation?
There's a calculation for it. There will be a ground bed of anodes associated with each power supply. There'll be multiple anodes, whether they're boreholes or along the length. Okay. So there's obviously a cabling issue because you've got to feed from your power supply to each set of anodes. Yeah. But you've got multiple, so it's called a ground bed, multiple blocks of anodes connected to the other end of the power supply. So this is the basic schematic of what's happening. In application, it's a bit more elaborate. Yeah. Okay. When you're looking at these systems and trying to design what's going on, there are loads of factors. One of the important things is to know whether you're trying to put CP on an old system or whether you're applying it to a new system. The age of the system is significant because the coating degrades with time. So what you'll see later on, I'll show you some data, the current requirement for an old pipe is higher than the current requirement for a newly coated pipe. You need to look at the soil conductivity because that has an effect on the magnitude of voltage you need to apply. It will impact on the IR drop, and we'll talk more about the on-off potential, which we briefly mentioned in our polarization section earlier on. You need to work out your current demand, and there are standards to relate that to, and we'll look at those very briefly in a minute. We need to think about our layout, number of anodes, where the test points are, and where we're going to isolate the system. So where are those insulation joints going so that we have a portion of pipe that we're going to control adequately. So I guess the first thing is to decide what system we're going to use, and more often than not we're going to use impressed current in onshore systems and sacrificial anode and offshore systems, but there are some parameters that you need to think about. For our sacrificial anode systems, the voltages are relatively low, the current is relatively low, and so you get less trouble with interaction with neighbouring structures, less stray current events. So that's good news from that point of view. But you need a fairly high conductivity environment for it to run well in. The impressed current system, they're not only more costly installation because you've got this wiring and the power supply and control unit and test points and the rest of it, but then you've got all the running costs because you've got to keep checking that system is working properly and the maintenance on the system as well. And we'll talk a little bit more about that in a minute, and we'll also talk about choosing the anode material as well. So there are quite a lot of things to think about in the system, but if you get the system right, you can operate it in quite complex and difficult environments where you couldn't necessarily use a sacrificial anode system. On your handout you've got this diagram which is a plot of soil resistivity against current demand, and all it's intended to say is that for higher resistivity, high current demand situations, then you need a power supply unit impressed current system. If you've got lower resistivity and lower currents, then the sacrificial anode will be fine, and that's all it's for. Okay. And if you just bear in mind it's all Ohm's law, I equals V over R, you won't go far wrong. And so if you've got a small voltage and a high resistance, it ain't going to work. Okay. So let's look at the impressed current system from general advantages. The systems are significantly higher voltage than our galvanic systems. Not only the voltage is higher, but the currents that can be supplied are higher, which means as you get more coating defects, the unit will be able to be cranked up to cope with them. not only can you monitor the voltage on the system, but quite often you can monitor the current that the power supply is using, and that's quite useful because if you remember, we've got our Faraday's law, our Q equals ZFM, and Q equals IT, so it's IT is the current times the time. And as you get more defects in the coating, the current will climb. So it's an indicator of what's happening generally on the system. If the current's climbing, that tells you the coating is beginning to degrade. The 48 volts, I haven't checked it, but I suspect that's because it's a multiple of 12, and that relates to the battery packs, okay? Because they're 2-volt cells of the multiplier, and they're supplied in 12-volt blocks. So I think that's why that's typically 48 volts. Yes, sir?
So this 48 volt is for each station
Yeah.
of the burst current?
Yeah, yeah. Sorry, yes. Okay. On the other side, yes, sir.
We're talking about quite high current values there. Is
Yeah.
there any risk? Let's say you have I mean, if you have a coated pipe, naturally it's more resistance. But if it's like a bare pipe, and you touch the pipe, is there any risk involved?
Yes. Of course, the pipe shouldn't be bare, and it should be buried.
Yeah. In the case where like you find a problem, you dig up, then you don't deactivate the ICCP system. So if like a worker goes in and touch the pipe, he says his life.
I think that's probably a bad idea.
Yeah.
And you should turn the system off first.
Yeah.
It's not something maybe one of the guys that have been involved with these systems can say, but I would think you turn them off before you work on them. Is that true? No. Shaking his head.
Yeah.
It's just, well, the press current system and the sacrificial anode system is not, it doesn't give you electrical shocks,
Yeah.
except it has interference with the AC system. Yeah.
Okay.
Is it because the voltage is too low in that sense? Like we're talking
Could
about
be.
voltages between like
Yeah.
48 to 100 volts.
Yeah, it's very low.
Some of the we haven't got any Americans here, have we? No. Some of the physicists say the reasons why the Americans have a 110-volt electricity system is so they don't electrocute themselves so much. They're just not as streetwise as the people who are using the 250-volt systems. But that's another story. Yeah. Okay. Thank you for that bit of input because, as I say, I'm more involved with theory than practice. Okay. We've got higher installation costs. We've got higher maintenance costs because we've got a load of checks to do on the system. So somewhere between about once a month to every quarter, we need to check the power supply, make sure that's all right. We need to go and have a look at the test points, make sure that's behaving itself, and we need to check if there have been any changes in the environment in terms of stray current. Okay, so you've got this regular monitoring of the system, and then annually you'd probably do a instantaneous current off test somewhere, going along the pipe, at least to the test points, if not in between. We'll talk about that in a minute. And you would check the connections so that you knew that your power supplies were actually doing the job both to the pipe and to the annex. So there's some annual maintenance and there's some more frequent checking going on. So there's quite a lot of cost. Because of the currents and voltages, we're going to get more straight current interactions. Because there's more control gear, then we're more liable to people fiddling with it, and we might also get situations of power failure, and that's a problem. And you can't just set one of these up. Generally, there's some planning to be approved for this sort of structure. This is just a note saying that there are various types of electrical interference. There's transient interference, which are things like these electric railways going past your pipe system. So every now and again you'll get as a train goes by, there will be a current flow between the conductors and the track, and that will then produce a field in the soil.
Excuse me.
Yeah.
What if there are any building or structures within the boundary where the current affects not only pipe but any other structures like this?
Anywhere where there's significant electrical field being generated can start interfering with your potential on your pipe.
And is there any method to protect those structures from the current from this irreversible causes?
Can you shield it? They tend not to do that sort of thing. I mean, it's a question of insulation, isn't it?
Yes, insulation for any other structure around pipeline.
Yeah. Pass. Anybody want to comment? No, nobody's going to comment. I think the answer's no. It's generally not done. People manage the current and potential on their pipe, and as long as they're aware of how much straight current they've got and what the interaction is, they try and manage it. So in the transient case, what you actually do is you put a recorder on the system and you monitor the potential with time and see what the average potential is on your pipe with time, and accept the spikes that you get as the train goes by. So it's trying to manage it rather than stopping it. Okay, it's one of those things you have to live with, I think, is the best way to look at it. Different people's pipes, different people's cabling and so on, buried around your own structure will give you sustained alteration to your potential current control. So you get transient and sustained. And then occasionally there are odd things that happen that give you a one-off shock to your system, whether that's a lightning strike or a power outage or a power spike. But those are instantaneous one-offs. Okay, so those are the three types of interference to your system.
So
yeah.
this electrical interference, affects the potential of your pipe?
Yeah.
Or does it?
So here's a bit of pipe with a pit in it
Yeah.
as a result of having lost the potential control.
Yes. So basically, the potential of your pipe increases, and then your power supply or
You've got to be careful about it, the word
Yeah,
increase.
Yeah. So it changes the potential of the pipe,
Yeah.
resulting in additional current being supplied. Is that it, or is it?
It may not be additional, it may result in less current
Less
being
current.
supplied because current has gone off to interact with another pipe.
Okay. So does this? Is this the same as stray current in that sense?
Yeah.
Yeah.
This is the sustained straight current, transient, and this isn't really straight current. It's some other electrical interference one-off into the system, whether that's loss of power or lightning strike, or so it could be a spike or a loss. Okay. The big question is, how much potential are we going to apply to the system? And what we'll see shortly is that there are some guidance to tell us what we should use. So we want to try and get a uniform potential along the pipe. That's almost impossible, but that would be the ideal. And that way we would be assured that we had got the corrosion under control. We tend to get some fluctuation we've got in potential, and we'll see that later on. But basically we're in a situation, if you don't apply enough CP, then you'll still get some corrosion. If you apply too much, then apart from wasting energy, you're also changing the local pH. It becomes alkaline around the cathode. That can have a negative effect on the coating. Okay, they don't like alkaline pHs particularly. And if you really overdo the CP, you'll start getting hydrogen, and that can cause delamination of the coating from the steel. So you get separation of coating and steel, which is not good, because later on you might get water ingress between the gap and then get crevice corrosion. Or perhaps even worse, you might get hydrogen absorption into the steel and get hydrogen embrittlement. which would be bad news. I'll show you this. You may remember it from earlier on. This was the handout I gave you of potentials against the standard hydrogen electrode. Just want to add to that this little bit of information here. Basically, for onshore measurements, most of them are done against the copper-copper sulfate electrode, and for offshore measurements, most of them are done against a silver-silver chloride electrode using seawater as the electrolyte. And the potentials for those I've actually written here against the standard hydrogen. There's the copper-copper sulfate down this side here. And so if you had that on an earlier handout, I can get you another one if you want it. Basically, the difference between these two electrodes is 50 millivolts. It's 48 actually, but it's 50 millivolts. So when you've got minus 800 to minus 900 copper-copper sulfate, which is giving you some protection, that's minus 750 to minus 850 in the silver-silver chloride seawater electrode. So it's 50 millivolts out on the shift for the zone of protection in the when you're using the other reference electrode. Yeah. Okay. So clearly we want to get into this cathode protection zone. We don't want to be over protecting the system. What we'll do next time is we'll look at the recommendations from the standards for onshore and offshore, and then maybe do a calculation of the current requirements. Thank you. Yes, sir.
Yeah. You said that the impress system usually suffers from vandalism, subcontract.
It can do because there's a lot more kit on the surface.
Yeah. I'm just wondering if you know you have an area prone to vandalism, can you use both interchangeably, the impress system and the sacrificial system on the same line?
Only if you isolate the individual parts. Yeah. So, yeah, you could isolate part of the line from the rest of it, and use sacrificial anodes on an isolated part. Yeah, but not in combination. And that would be, I mean, it would be a it'd be a nightmare to manage apart from anything else. Can you imagine the two sets of fields? So on individual sections along the pipe, you can change your technique, but you can't use them in combination at one point. Okay. There are all sorts of things that, I mean, vandalism is one of those odd descriptions. There are things like somebody decides to cut one of your cables because they're digging a trench for some other purpose. You know, it can be construction work, other things happening as well. So, any urban area. Okay.
Quick follow-up question on this, because basically I've talked to some consultants about the idea of this inverse current system. Is what they're telling me is, in terms of the anode has a range of what they throw the current to. That means they can throw the proton.
It's called current. It's called current throw.
Yeah.
All electrodes have a current throw.
So there is like a radius or that they can reach.
Yeah.
So is there a limitation? What controls the range of this?
The soil resistance.
The soil resistance.
Yeah.
So it links back to my question just now. So basically, you need to do a bit of layout planning to place your anode so that the entire part is.
You have to know what environment you're putting it into.
But is there any rough number we can take a guess at, like what a typical titanium electrode? How far can it throw?
there'll be data in the standards.
So
Yeah.
standards will
Yeah.
have this kind of
Yeah.
information. Okay.
Thank you.
You were saying regarding the applications, onshore, offshore.
Yeah.
Which one is onshore impressive?
So, buried pipes onshore usually in press current, offshore usually sacrifice lanyard. Just because the conductivity of the seawater is so much higher, and you don't have a load of electrical problems of trying to get a power supply unit out in the middle of an offshore oil well or something like that.
I never seen this technology. Find out.
I mean, there are. It's a rule of thumb. It's not to say that you never find an impressed current system out in offshore. You do, but commonly you use the galvanic system.
Yeah, I think we also use because I haven't checked offshore pipelines.
Right.
So I don't know what kind of CT system they're using. Just asking.
Yeah, it'd be interesting to see. When did you check for those papers?